In the last period, we have studied about the reactivity towards halogen. So let's start the revision. Meanwhile, so let's study about the reactivity towards halogen. Uh, Element of group 14, which are carbon, silicon, germanium, tin, and lead, they form two type of halides, either MX2 type of or MX4 type of. All the other carbon, except carbon, all the other members react directly with halogen under suitable condition to make halides. Most of the MX4 are covalent in nature. The central metal atom in these halides undergo sp3 hybridization and their shape would be tetrahedral. This is what we are talking about MX4 type of halides. Now we have some exceptions. SNF4 and PbF4 are ionic in nature. Why should they be ionic in nature? Because they are the metal fluorides, and that is why the electronegativity of fluorine is very high. Thus, they turn ionic in nature. Due to high electronegativity difference between fluorine and lead or fluorine and tin, they are ionic in nature. Remember, this is the kind of questions that can be even asked, that why lead fluoride, lead tetrafluoride and tin tetrafluorides are ionic in nature. So this is how you can answer that. Due to the high electronegativity difference between fluorine and lead or fluorine and tin, uh, this type of fluorides like lead tetrafluoride or tin tetrafluorides are ionic in nature. Remember that PbI4 does not exist. Now, why PbI4 does not exist? Let us understand the answer, my dear students, that because PbI bond initially formed during the reaction does not release enough energy. Remember once again, PbI bond initially formed during the reaction does not release enough energy to unpair the 6s2 electrons and exit one of them to higher or by excite and excite one of the electrons present in 6s2 to go to the higher orbital to have unpaired electron around the lead atom. So this PbI4 is not possible. PbI4 is not possible because um, the PbI bond, once if it is formed, it does not release enough energy to unpair this 6s2 electron. So we can simply say that it is because of the inert pair effect. Now let's move forward. Heavier members such as germanium, tin, lead are able to make halides of formula MX2. So please remember that germanium, tin and lead only they make the MX2 type of halide. Stability of this type of halides increases going down the group. Considering the thermal and chemical stability, GEX4 is more stable than GEX2. SNX4 is more stable than SNX2, but please remember, but PbX2 is more stable than PbX4. So in Pb or in the last element, we are well aware that Pb plus 2 is more stable than Pb plus 4. But in case of germanium, Ge plus 2 is less stable than Ge plus 4, or for tin, Sn plus 2 is less stable than Sn plus 4. Except CCl, for all the other tetrahalides are easily hydrolyzed by water because of the central atom can accommodate lone pair of electron from oxygen atom of water molecule in the d orbital. Hydrolysis, so we are well aware that the first element of this group, that is carbon, and it has unavailability of vacant d orbitals. So as it has unavailability of vacant d orbitals, this is how it takes place. Hydrolysis can be understood by taking the example of SiCl4. It undergoes hydrolysis by initially accepting the lone pair of electrons from water molecule in the d orbitals of Si, finally leading to the formation of SiOH4 as you can see here. See, first we have SiCl4 which reacts with water. So one molecule of HCl is being removed and we get SiOHCl3. This is how we can write it as this SiOHCl3. So one of the Cl is being replaced by the OH group. Same way when the process going on and three other water molecules react with the three other molecules of SS. So finally three HCl molecules are being removed and we get SiOH4. This SiOH4 is known as the silicic acid, and this is how we can understand the hydrolysis of the SiCl4 or tetrahalides. So tetrahalides can be hydrolyzed to give tetrahydroxo product. Please remember, my dear students, carbon CCl4 does not undergo the hydrolysis because there is non-availability of the d orbital into that. Then we have the question. Please pay attention. SiF6 minus 2 is known, whereas SiCl6 minus 2 is not known. Give possible reason. So let us understand the possible reason, my dear student. The main reason are 6 large chlorine ions cannot be accommodated around the Si plus 4 due to the limitation of its size. And interaction between the lone pair of chlorine ion on Si plus 4 is not very strong. So now let me explain. SiF6 minus 2 is possible or it is known, but SiCl6 minus 2 is not known. Give reason. So first of all, you can understand that around the small, around the Si, there are possibility of accommodating 6F minus. So 6F minus can be accommodated, and as this 6F minus can be accommodated around Si, we can have SiF6 minus 2 possible. But at the same time, if you want to prepare SiCl6 around a very small Si, my dear students, around small Si, it is difficult to accommodate the 6Cl. The Cls are comparatively bigger in size, so it is difficult to accommodate them. And thus, when it is difficult to accommodate them, it is really difficult to make SiCl6 minus. There is one more interesting reason that we can even understand, and that reason is this: that this reason is very simple to understand, my dear student, that interaction between the lone pair of chlorine ion and Si plus 4 is not very strong. So when the interaction itself is not very strong, my dear students, they do not prefer to make any kind of bonding, and thus we can say that SiCl6 minus 2 does not get possible because of the weak interaction between the lone pair of chlorine and the Si plus 4 ion. Then important trends in anomalous behavior of carbon. This is very important, my dear students. We know that the first element of any group, if it belongs to second period, it shows the anomalous behavior. So let us see how carbon is different from the other members of the same group, that is group number 14. Like first member of the other group, carbon also differs from the rest of the members of the group. So please remember that carbon even differs from the rest of the members of the group. So how does it differ? And why? First of all, let us see why does it differs. Because of the smaller size, higher electronegativity, high ionization enthalpy, and unavailability of the vacant d orbitals, carbon is different from the other element of the same group, that is group number 15. Why covalence of carbon is limited up to 4? Why carbon can make maximum 4 bond? In carbon only S and P orbitals are available. If you look into the carbon, my dear students, atomic number 6, atomic mass number is 12. So if you can write the electronic configuration of carbon as helium 2s2 2p2. You know that here n is equal to 2 and 2d is not possible, so d orbitals are not available, and that is why we can say that carbon has only s and p orbitals, d orbitals are not available. So in carbon only s and p orbitals are available for bonding, and therefore it can accommodate uh, only 4 pairs of electron around it. How 4 pairs of electron? So you can see that in 2s we have 1 orbital and in 2p we have 3 orbital, and thus 1 plus 3 is equal to 4. Thus only 4 pairs of electron can be accommodated into the carbon, and that is why its covalency can be maximum 4. This would limit the maximum covalence of 4, whereas other members can expand their covalence due to presence of the d orbitals. Carbon has a unique ability to form pp bonds, pp multiple bonds with itself and with other atoms of small size and high electronegativity. Now please understand, my dear students, that if there is a pp bond which is a multiple bond, it is formed by the sideways overlap. When the bond is formed by the sideways overlap, it is very much necessary that the elements present, they come very closer. See, this is the if this is one of the carbon, my dear student, if this is one of the carbon, and then we have the another oxygen, let us say, then they will have to come quite closer. So the size of this element should be very small. Now, if you think of the d orbital and then the sideways over of this, then you can see that this distance between carbon and any other element, let's say E, become little longer. So please understand that for making the pp kind of bond, the atoms must be small in size. These atoms should be small in size. So these atoms should be small in size. And they should have high electronegativity. So when pp bond are formed, the atoms must be small in size and they should have the higher electronegativity. For example, carbon 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 double bond carbon carbon triple bond carbon, here 1 pi bond, here 2 pi bonds, pp kind of bonds, here 1 pi bond, here also we have uh, here also you can have uh, 2 pi bonds. So this is possible when the atoms are very small. Heavier elements do not form pp bond because their atomic orbitals are large and diffused. Their atomic orbitals are definitely large and they are diffused to have effective overlapping. Why heavier elements do not form pp bond? If this kind of question is asked, you can answer these questions that heavier elements do not form pp bond because their atomic orbitals are too large. Their atomic orbitals are too large, my dear students, and as their atomic orbitals are too large and diffuse, they cannot make a pp kind of bond. For making pp kind of bond, the atom should be very small in size and they should have the high electronegativity. Please remember that to make the pp kind of bonds, the atom should be very small in size and they should have the large electronegativity. Now, dear students, we want to study about the catenation. We have studied about catenation in 10th standard too, but let us look at the definition of catenation. Carbon atoms have tendency to link with one another through covalent bond to form chains and rings. This property is called catenation. Please remember that carbon atoms have tendency to link with another through covalent bonds. To form chains and rings, this property is known as the catenation. Carbon show catenation tendency because what is the reason? Let us look at number one. Carbon-carbon bond is very strong, and this can be expressed using the bond enthalpy, and the bond enthalpy of carbon-carbon bond is 348 kilojoule per mole. So there are two reasons. One, we can say that carbon bond is very strong, and this we can prove by writing the bond enthalpy of 348 kilojoule per mole, and that is why this carbon-carbon bond is very stable. It can form the long chains, branched chains, as well as the rings, and thus carbon shows the highest catenation property. Going down the group of 14, my dear students, why tendency to show catenation decreases? Let us answer this question. Going down the group 14, the size increases, electronegativity decreases due to above two reasons. Tendency to show catenation decreases. So once again, why the property of catenation decreases going down the group? Going down the group, the size increases, electronegativity decreases, and due to above two reasons, the tendency to show catenation also decreases. This can be clearly seen from the bond enthalpy values. So if you look into the various bond enthalpy values, you can see for carbon-carbon it is 348 kilojoule per mole. For silicon-silicon it is 297 kilojoule per mole. For germanium-germanium it is 260 kilojoule per mole. For tin-tin it is 240 kilojoule per mole. My dear students, our lead is a typical metal, and that is why we need not to discuss the catenation property for the metals. But here we can see that the highest catenation property is with the carbon-carbon. You can see there is a vast difference between the bond enthalpy value of silicon and carbon, but still 297 is a good or higher value, and that is why silicon also show considerable amount of catenation. But as you go down the group, you can see that germanium and tin, they also show catenation, but their catenation property is comparatively very less as compared to the catenation of carbon. The order of catenation property, my dear students, the order of catenation property decreases. You can see that carbon has got very high catenation property than germanium, and germanium and tin have almost the same or similar kind of catenation properties. Lead does not show catenation because it is a metal, and metal catenation is not a characteristic of metal. Due to the property of catenation and pi-pi bond formation, carbon is able to show allotropic forms. So please remember, why, suppose someone asks you why carbon shows allotrops or why the element shows allotrop. So those elements which have ability to make the pi-pi bonds or to make multiple bonds at the same time, if they have a very strong bond, they generally show the allotrops. Do you know, my dear students, which elements show the allotrops? Students, I am asking you, dear students, do you know which
Carbon.
elements show the allotrops?
Carbon.
Apart from carbon? See, apart from carbon, phosphorus show, sulfur. So this is how you can understand that phosphorus and sulfur, even our arsenic, tin, antimony, this also shows the allotropic forms. I hope you understood. Okay, now my dear students, we are going to study about the allotrops of carbon. So whatever we have discussed, my dear students, now if you have any doubt, you can ask me. Is there anything which you could not understand? You can ask me the doubts, or then we can move towards the allotrops of carbon. This is the part of this chapter which we have already studied in 10th standard 2. Dear students, was there anything which you could not understand? You can ask me. Hello. Will you please answer? What you can read on your screen? Are you able
दिख
to
रहा है
see the
सर.
screen properly? That's what I'm trying to asking you. What you can see on the
Yes sir,
screen?
properly दिख रहा है सर.
Huh?
Allotropes of carbon sir.
Okay, okay. So now let's move and study about the allotropes of carbons. Carbon exhibits many allotropic forms, both crystalline as well as the amorphous. Diamond and graphite are two well-known crystalline forms of carbon. In the year 1985, third form of carbon known as fullerene was discovered by H. W. Croto, E. Smalley and R. F. Curl. For this discovery, they were awarded the Nobel Prize. Now, dear students, let us study about the diamond. Diamond, it has a crystalline lattice. So please remember, diamond is the crystalline form of carbon. Crystalline allotrop or form. In diamond, each carbon atom undergo sp3 hybridization and linked to four other carbon atoms by using hybridized orbital in the tetrahedral fashion. So you can see that due to sp3 hybridization, each carbon is bonded to the four other carbon and they have the tetrahedral shape. The carbon-carbon bond length is 154 picometer. If you can remember this, please remember this bond length. It may be useful in future. The structure extends in space and produces a rigid three-dimensional network of carbon atom. I hope you can see this rigid structure of carbon atom. Let me show you. Is it there on your screen? Can you see the structure of the carbon atom?
Yes, sir.
Yes, sir.
Very good, my dear students. Thank you for the reply. So this is how you can see that this one carbon is bonded to the 1, 2, 3 and 4 other carbons with sp3 hybridization, and the shape you can see it is tetrahedral. So my dear students, we have this carbon. You can see that this bond length is 154 picometer, which is the carbon-carbon single bond, and this kind of web-like structure is formed. It is web-like structure. You can see that this is a giant molecule of giant molecule. It is a very big molecule of carbon. You don't know what is the number of carbon present in this. So this is how this is a giant molecule. It is the hardest substance in the world. No other substance is so hard as carbon in this, so hard as diamond. And that is why diamond is used as an abrasive. It is used into the cutting tool. Especially it is used to cut the glass, and only diamond can cut diamond. Apart from that, my dear students, due to these wave-like structures and a very giant molecule, when the light falls on diamond, it undergoes the multiple, multiple, the light undergoes the multiple reflection. And due to this, my dear students, the diamond starts shining when the light falls on it. And as due to this, my dear students, the diamond is used into the making of the various jewelries. Let us study more about, or let us look into the text. In the structure, my dear students, or in the above figure, you have studied about the diamond. Uh, Structure directional covalent bonds are present throughout the lattice. You can see that throughout the lattice of diamond, it is very difficult to break extended covalent bonding, and therefore diamond is the hardest substance on the earth. It is used as an abrasive. Abrasive means cutting tools. Abrasive is something that cuts the other substances. For sharpening hard tools, in making dyes, and in the manufacture of the tungsten filaments for electric light bulbs. So these are the uses of diamonds. Once again, I would like to share with you all the uses of diamonds. Due to it is very difficult to break the extended covalent bonding in diamond, and therefore number one, diamond is the hardest substance on the earth. Number one, diamond is used as an abrasive. Number two, Diamond is used for sharpening the hard tools. Number 3, diamond is used in the making of dye. Number 4, diamond is used in the manufacture of tungsten filament for electric light bulbs. So these are the 4 various uses of diamond you can learn, my dear students. Then we have a question. Diamond is covalent, yet it has high melting point, and what is the reason? Diamond is covalent, yet it has high melting point. What is the reason? Diamond has a three-dimensional network involving strong carbon-carbon bonds, which are very difficult to break, and in turns has a high melting point. So what is the reason that diamond has a high melting point? Let me repeat once again for you, my dear students. Diamond has a three-dimensional network involving strong carbon-carbon bonds, which are very difficult to break, and in turns, diamond has a high melting point. So this is how we can understand that diamond has a high melting point. Now, my dear students, we are going to study about the graphite. Please remember one more thing that I would like to share with you is that diamond has got a very high refractive index. Diamond has high refractive index. And this is even one of the reason why the light in diamond undergoes multiple reflections, and that is why the diamond shines and it is used into the making of jewelries. Now, my dear students, we are going to study about the another allotrop of carbon, which is known as graphite. So let us study about graphite, my dear students. Graphite has a layered structure. Layers are held together by the van der Waals forces, and distance between the two layers is 340 picometer. Each layer is composed of planar hexagonal rings. Please remember, each layer is composed of planar hexagonal rings of carbon atoms. Carbon-carbon single bond length within the layer is a 141.5 picometer. Each carbon atom in the hexagonal ring undergoes sp2 hybridization and makes three sigma bonds with three neighboring carbon atoms. Fourth electron forms a pi bond, and the electrons are delocalized over the whole sheet. Now please remember that in graphite, my dear students, we have sp2 hybridization. If you look into the carbon, we have the electronic configuration helium 2s2 2p2. So it is in this form, this is 2s2, and then we have in 2p, my dear students, we have only two orbitals present. When carbon goes excited, my dear students, the in the excited state, carbon has this kind of condition. So one electron from 2s goes to the 2p, and then we have the four vacant d orbital, but only 1s and 2p orbitals, if undergoes the sp2 hybridization, this orbital or this electron does not take part into the hybridization. As this electron does not take part into the hybridization, it becomes the fourth electron. See, 1, 2, and 3 and 4. The fourth electron forms a pi bond. So thus, when two carbon make the bonding with each other, here also carbon combines with each other. This carbon with this carbon forms a pi bond here. This carbon with this carbon forms a sideways overlapping and forms the pi bond. So fourth electron forms a pi bond. If it does not form pi bond, think, if it does not form pi bond, the electrons are delocalized over the whole sheet. So we can say that it makes the pi bond and then it is delocalized, or even if it remains free, it is this fourth electron of each carbon. Remember, fourth electron of each carbon is delocalized over the whole sheet. These electrons are mobile. They can move easily. Mobile means they can move easily. So these electrons are mobile. Now you will understand it better. Let me explain uh, the formation of graphite to you. Now you can see on your screen, my dear students, you have the picture of graphite. You can see in graphite, my dear students, In graphite, we have the various carbon atoms bonded to each other. You can see that each carbon atom, this carbon atom is bonded to three other carbons, 1, 2 and 3. That means that only 3 valency of carbon is utilized. The fourth valency or fourth electron is either used to make pi bond, which is delocalized. The electron is delocalized. The electron is free or mobile. This free or mobile electron is used to make graphite good conductor. Good conductor. So graphite is a good conductor of heat and electricity, especially graphite is a good conductor of electricity because this fourth electron which is used to make the pi bonds is delocalized all over the sheet. This mobile is free, this electron is free, this electron is mobile, and that is why it helps to pass the electricity, and that is why this fourth electron, which is not used into the making of the sp3 hybridization, is responsible for a conducting nature of graphite, and graphite is a good conductor of electricity. Please remember that the carbon-carbon bond length in graphite is 141.5 picometer, but these layers of this carbon, they form the hexagonal structures, and these hexagonal layers are separated with each other. These hexagonal layers are attracted by the van der Waals forces. Van der Waals forces. So please remember that these two layers are, or this layer and this layer, even this layer and this layer, they are attracted by each other with the van der Waals forces. The distance between these two layers is 340 picometer, and these electrons which are free, they are delocalized in these layers, and that is what it makes the graphite a good conductor. Now, my dear students, you even need to understand that if you apply some pressure, if you apply some pressure on this layers, think if we apply some pressure. When we apply some pressure, my dear students, what happens? These layers, when we apply some pressure on these layers sleep over each other. When we apply the pressure from outside, these layers sleeps over each other. So this layer move in this direction and this layer moves in this direction. Due to that, what happens? This graphite is soft. As the layers can sleep over each other, the graphite is soft. So we can say that graphite is soft. We can say that the layers of graphite can sleep over each other, and that is why graphite can be used as a lubricant. Graphite can be used in the pencil. So when we apply pressure to the pencil, the layers of graphite sleeps over each other. Let me explain this to you, my dear students. So what we have seen here, dear student, is that graphite has layers. These layers of graphite have some distance of 340 picometer. These layers are attracted by weak van der Waals forces. As these layers are attracted by weak van der Waals forces, when the pressure from outside is applied, what happens? These layers slips over each other. Now, as these layers can slip over each other, my dear students, we can have the various characteristics or various uses. Thus, what happens? Graphite is soft. As graphite is soft, my dear students, graphite can be used in pencil. Used in pencil. Why graphite is used in pencil? Because in the pencil lid, when you apply the pressures, the layers of graphite, when you apply the pressure in pencil, the layers of graphite, they comes on paper, and thus we can write, and that is how graphite is used into the pencil. Same way, graphite is used as a lubricant. Lubricant is a kind of substance that is used to give lubrication to the machine parts which are there or which are feel the friction with each other. Now there is one more speciality of our graphite. What is the speciality? Let us look at. Graphite has high melting point. If even we do not think about the high melting point, we can think and boiling point. Thus, when the other lubricants become vapor, graphite can be used as a lubricant even at higher temperatures. So, graphite can be used as a lubricant even at a higher temperature. So please remember, my dear students, that graphite has layers. These layers have some 340 picometer resistance. These layers are attracted by weak van der Waals forces, and thus when we apply pressure from outside, these layers can slip over each other. When these layers can slip over each other, that is why graphite is soft and it is used into the pencil, because when we apply pressure, the layers of graphite comes on the paper and we can write. Graphite is soft, and that is why its a layer slip over each other. That is why it is used as a lubricant. But graphite has got very high melting point and boiling point. So when the other lubricants turns into vapor, this graphite is still able to provide lubrication, and that is why graphite is even used as a lubricant even at higher temperature. So I hope, my dear students, you understood this. Do you have any doubt? बच्चों आपकी समझ में आ गया है? Have you got it?
Yes,